Welcome back. Today's goal of this lecture, in my previous video, I had discussed what is the Liouvillie theorem in complex analysis. Just as a review, the statement of Liouvillie theorem is a function which is analytic and bounded in the whole plane. That implies obviously the function must be constant. Another exercise of Liouvillie theorem is a bounded entire function is constant. Also in my previous video I had seen if real fz or imaginary fz is bounded, that implies the function fz is constant. Today's goal of this lecture, today I will at first see some more exercise about Liouvillie theorem, then I will see a generalized version of Liouvillie theorem. This is the today's goal of this lecture. But at first I will highly recommend you, if you don't see my previous video, at first see my previous video, then today's video would be so easy. Okay? Let's see some exercise about Liouvillie theorem. First exercise, let f be an entire function and the condition is such that modulus of fz greater than equal to m, and this is true for all z belongs to complex number. Then that implies f is a constant function. Since here f be entire function such that modulus of fz greater than equal to m, and we have to prove f is constant, consider fz not equal to 0. Because if fz equal to 0, then that violates this condition, because here given modulus of fz greater than equal to m, and this is true for all z belongs to complex number. Now consider gz equal to 1 over fz. Obviously, since f be an entire function given, so this is an entire function. Then modulus of gz equal to modulus of 1 over fz, then this value is 1 over modulus of fz. And since given modulus of fz greater than equal to m, that means 1 over modulus of fz, this is less than equal to 1 over m, and this is true for all z belongs to complex number. That implies gz is bounded. Here I will apply the Liouvillie theorem. Since gz is entire, also I have got gz is bounded. So by Liouvillie theorem, we can tell gz is constant function. Consider gz equal to alpha, where for all z belongs to complex number. That means 1 over fz equal to alpha. So this is true for all z belongs to complex number. So that implies fz is a constant function. I hope my all viewers have understood this is clearly. Okay? Oh well. Second, let f be entire function such that image of the function is not contain a disk, then that implies the function is a constant function. That means the disk here such type, because the image of the function is this. This is the image of the function, and this is the disk. Here disk does not contain this image of f. Therefore, since disk does not contain image, so fz minus z0, this is not equal to 0, and this is true for all z belongs to C, because here the disks contain the point with respect to z0 with radius r. Then second, absolute value of fz minus z0, this value is greater than equal to r, and this is true for all z belongs to complex number. Then zz equal to, since consider zz equal to 1 over fz minus z0, and here this is greater than equal to r because these disks does not contain image of f. So image distance between fz and these disks always would be greater than equal to r. So I have considered zz equal to this. Therefore this is less than equal to 1 over r, and this is true for all z belongs to complex number. Here absolute value of zz. Therefore, since I have got modulus of zz less than equal to 1 over r, and this is true for all z belongs to complex number, obviously since f be entire function given, therefore zz is obviously entire function which is bounded. So similar to before by Liouvillie's theorem, we can tell zz is constant. I hope my all viewers have understood this is clearly. Okay. Next example, which had come next. This question had come in CSIR NET exam, and the question is, consider the set f which is defined from complex number to complex number such that f is an entire function, and here given absolute value of f prime z less than equal to absolute value of fz, and this is true for all z belongs to complex number, then which of the following is true? Option 1, f is a finite set. Option 2, f is countably infinite set. Option 3, f equal to b to the power az, where b belongs to complex number and alpha belongs to complex number. And option 4, f equal to b to the power az, where b belongs to complex number and absolute value of alpha belongs to complex number. Since here given f prime z, absolute value of f prime z less than equal to fz, then that imply absolute value of f prime z over absolute value of fz less than equal to 1, and this is true for all z belongs to complex number. Here by this condition fz not equal to 0, and this is true for all z belongs to complex number. Here given f is an entire function, that imply f modulus of f prime over fz, this is f prime over f, this is an entire function. And since f prime of over f, this less than equal to 1, that means here this is entire, and by this is bounded. Entire plus bounded, that imply constant function. Therefore f prime over f equal to constant c, that imply log fz, if we integrate both sides, then that imply log fz equal to cz plus d. And this imply fz equal to e to the power cz plus d. And this is means e to the power cz times e to the power d. Now notice the option. Option 3 imply f equal to beta e to the power az, where beta belongs to complex number and a belongs to complex number. And option 4 indicate f equal to beta e to the power az, where beta belongs to complex number and absolute of a less than equal to 1. Which of in 3 which be the correct option? Notice here I have got fz equal to beta e to the power az. Obviously beta belongs to complex number. For second condition, absolute value of f prime z over fz less than equal to 1. If you put f prime z means a b to the beta e to the power az, and fz means beta e to the power az. Now cancel this part, then this value would be absolute value of a less than equal to 1. Therefore, I have got f equal to beta e to the power az such that beta belongs to complex number and absolute value of a less than equal to 1. Option 4 is a right option. And obviously, this would be a less than. Since beta belongs to complex number, so obviously this f is countably infinite set. That means 2 and 4. Option 2 and option 4 is the right option. I hope my all viewers have understood this type of question easily. Okay? Well. Now I will see what is the generalized versions of Liouvillie theorem. And enter function f which satisfies modulus of fz less than equal to m times modulus of z to the power alpha, where for some alpha greater than equal to 0 and m greater than 0 and all sufficiently large mod z reduces always to a polynomial of degree n, where n is the largest integer such that n always less than equal to alpha. I hope my all viewers have understood this is. For this generalized Liouvillie theorem, first lemma 1 is, at first I will see two lemma which actually depends on generalized versions of Liouvillie theorem. First lemma, a non-constant polynomial is actually unbounded. Second, a non-constant polynomial with complex coefficient has at least one zero. And the proof is such type. Let a be a non-constant polynomial. Here we have to prove it has at least one zero. But I will prove it by contradiction. Consider fz has no zeros. That means fz not equal to 0. This is true for all z belongs to complex number. Now consider g equal to 1 over f. And since f is non-constant polynomial function always be analytic. So g is analytic in the whole plane. Then limit z goes to infinity gz equal to limit z goes to infinity 1 over fz, and this value is always 0. We all of us know. So by definition of limit, for every epsilon greater than 0, there exists r greater than 0, such that mod z less than epsilon, and this is true for all modulus of z less than r. Therefore, from this we can tell z is entire, because this is analytic in the whole plane, so z is obviously entire, and bounded on the compact sets mod z less than r. Therefore, that imply by Liouvilie's theorem, we can tell f equal to 1 over z, this is reduces as constant function. But here given, this is f be a non-constant polynomial. Therefore, our assumption is wrong. Here I have assumed fz has no zeros. But if we consider fz has no zeros, then this reduces as constant function. This violates our assumption. So, a non-constant polynomial with complex coefficient always has at least one zero. I hope my all viewers have understood the proof. Okay? Oh well. And we all of us know this theorem is actually known as the fundamental theorem of algebra. The theorem is a non-constant polynomial with complex coefficient has always at least one zero. This is called the fundamental theorem of algebra, we all of us know. Now I will see what is the actual generalized Liouvilie's theorem. Let f be entire function, then there exists positive constant a and b such that absolute value of fz less than equal to a plus bz to the power n, where n equal to 0, 1, 2, so on. Then that implies, obviously, this f is a polynomial at most degree n. When n equal to 0, then the theorem reduces. Liouvilie's theorem. Now I will prove for n equal to 1. Now we prove for n equal to 1. Now consider a function as gz equal to fz minus f0 over z minus 0. This is true for all z not equal to 0 and f prime 0. This is true for all z equal to 0. Notice, since f be entire function, z also be entire function, so their division also be entire function. So, fz minus f0 over z minus 0 means fz over z. Obviously, this function be entire because f is entire, and when limit z tends to 0, then this value would be f prime 0. So, obviously, whole g is entire function. I hope my all viewers have understood. And since g is entire, that means g is continuous. So, if we consider mod z less than equal to 1, then in this compact set, since g is continuous, g would be bounded. Then consider for mod z greater than equal to 1. Now we prove for n equal to 1. Now consider a function as gz equal to fz minus f0 over z minus 0. This is true for all z not equal to 0 and f prime 0. This is true for all z equal to 0. Notice, since f be entire function, z also be entire function, so their division also be entire function. So, fz minus f0 over z minus 0 means fz over z. Obviously, this function be entire because f is entire, and when limit z tends to 0, then this value would be f prime 0. So, obviously, whole g is entire function. I hope my all viewers have understood. And since g is entire, that means G is continuous. So, if we consider mod Z less than equal to 1, then in this compact set, since G is continuous, G would be bounded. Then consider for mod Z greater than equal to 1. When modulus of Z greater than equal to 1, then mod Cz equal to mod Fz minus F0 over Z minus 0. And this is less than equal to by triangle inequality, less than equal to mod Fz plus mod F0 divided by mod Z. And since mod Fz less than equal to a plus z mod z to the power n, here I have considered n equal to 1. So this value would be a plus b mod z, and mod z over mod z mean this value would be just b. That means this value is less than equal to a plus mod f0 over mod z plus b. And since this condition for mod z greater than equal to 1, that means 1 over mod j would be less than equal to 1. So this value is less than equal to a plus modulus of f0 plus b. And that implies when mod z greater than equal to 1, then g is bounded for mod z greater than equal to 1. That means I have got for mod z less than equal to 1, g is bounded. Also mod z greater than equal to 1, g is bounded. Then that means g is, since g is entered, that means g is continuous in whole complex plane. G is bounded on this compact set. And also I have got g is bounded in this compact set. In this set mod z greater than equal to 1. So G that implies G is bounded in the whole plane. Hence by Liouvillie's theorem we can tell Gz equal to constant. So for some constant k1 and for all z belongs to C, since Gz equal to constant and Gz means Fz minus F0 over z, so that implies Fz equal to k1z plus f0, and this is be a polynomial of degree 1. So I have got when n equal to 1, this is be a polynomial of degree 1. Then for n equal to 2, I will prove this result is true for n equal to 2. Since the result is true for n equal to 1, then for mod z less than equal to 1, modulus of Gz less than equal to a1, and since this is true for n equal to 1, so we can write this is less than equal to a1 plus b modulus of z. For mod z less than equal to 1, I have got mod gz less than equal to a1 plus b1 mod z. Also for mod z greater than equal to 1, I have got mod gz less than equal to a2 plus b2 mod z. So consider C, which is maximum of a1 a2. Also consider D, which is maximum of b1 and b2. For mod z less than equal to 1, I have got mod gz less than equal to a1 plus b1 mod z. Also for mod z greater than equal to 1, I have got mod gz less than equal to a2 plus b2 mod z. So consider C, which is maximum of a1 a2. Also consider D, which is maximum of b1 and b2. Consider C equal to maximum of this a1 and a2 and D equal to maximum of b1 and b2. Then mod gz would be less than equal to C plus D mod z. That implies mod z equal to k2z plus k3. That implies Gz equal to k2z plus k3. And Gz means Fz minus F0 over Z minus 0, which is equal to K2 plus K3. Therefore, that imply Fz equal to K2Z square plus K3Z plus F0 for some constant K2 and K3. That means F is a polynomial of degree 2 at most 2. I hope my all viewers have understood. Therefore, when n equal to 2, that imply F is polynomial of degree 2, degree at most 2. Therefore, by induction we can tell G is polynomial of degree at most n minus 1 and F is polynomial of degree at most n. I hope my all viewers have understood this is clearly. Okay. Well, therefore, when F is entered, then there exists a positive constant a and b such that modulus of Fz less than equal to a plus b modulus of z to the power n. Then that imply F is a polynomial of degree at most n. I hope my all viewers have understood this is actually the generalized version of Liouvillie's theorem. Okay? Well, I will stop here. In my next video, I will see some more exercise about general version of Liouvillie's theorem. Okay? See you soon. Stay safe, stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.